Hey there, my chem kids. We are going to do our notes on kinetic molecular theory, and it ties into our Skittles activity. I kept asking you why, as you know, that's my favorite question. Why did the colors dissolve? Why didn't they mix? Why did they flow the way they did? Why did they even flow? And yes, IMS, intermolecular forces, are at play now, and I think you have a grasp of that. So the intermolecular forces in the water interact with the dye, help it dissolve, but it doesn't quite explain the expansion of the color throughout the liquid, etc. So let's go ahead and take our notes. So you should have your white notes packet out at this point, and we're going to follow along with that. So for kinetic molecular theory, it's about, just its name is very self-explanatory. It's the theory about the movement of molecules. And in order to make our understanding easier, we have 5 assumptions that we go through that are mostly true. Assumption number 1 is that gases consist of particles that are like marbles, but really, really tiny. So they're far apart, and because they are so far apart and so small, they essentially don't see any of the other molecules. So from their point of view, those other molecules don't exist. So we can assume that they're so tiny, they have zero volume within the container. Now, obviously that's not true, but again, it's an assumption based on the fact that they're small and far apart. Assumption number 2 is that anytime they do collide, if they happen to collide, their collisions are perfectly elastic. Think about pool balls colliding. They bounce off each other really fast, and they don't just stop, they keep moving. That transfer of kinetic energy is not quite 100%, but the idea in molecules is that if they do collide, it is transferred 100%. We don't lose kinetic energy. Think about if you held a tennis ball at shoulder height, you opened your hand. If it was a perfectly elastic collision with the ground, it would pop right back up into your hand and you could catch it. That's a perfectly elastic collision. Ideal. There's no loss of energy and heat or friction. We know that's not necessarily true. We do lose kinetic energy in the real world. But for our assumptions for K and T, that's what we assume. Third assumption is that constant random motion. Molecules never stop moving. Period. At 0 Kelvin, yes, but we never reach 0 Kelvin, so even at 0.0001 Kelvin, they are still moving. And they possess kinetic energy because kinetic energy is the energy of motion. Assumption number 4, gas particles are not attracted to one another. Well, they're not attracted to one another. That means there are no IMFs. And essentially why we can assume that is because they are moving so fast that even if they were to come close to one another, they're moving so fast that any attractive force is basically non-existent because the motion has them slide past one another before the IMF can even come into play. Assumption number 5 is that temperature is related to kinetic energy. So in what you see here is a low energy sample of gas. That's why they did it blue, and the little movement marks are smaller. When you heat it up, they're going to move faster, so higher kinetic energy. And that's kind of logical. I think we all kind of can understand that. And we can calculate kinetic energy by doing Ke is kinetic energy, 1/2 mv squared, where m is mass and v is velocity or speed, and we square that. So there is a direct relationship between kinetic energy and the velocity. There is a direct relationship between kinetic energy and the mass. The higher the mass, kinetic energy goes up, but the speed goes down because it is more massive. Think of inertia. We're not going to do the simulation. We'll investigate that in class. So this kind of graph is very popular when we're talking about temperatures of samples of gases. Don't worry about this label over here. Essentially what it's saying is this is one sample of gas at a lower temperature, and the area under the curve, if you were to integrate that, represents the number of particles in that sample of gas. It's at 80 Kelvin. If we take that same sample of gas, that green represents the same sample of gas at 300 Kelvin, we can see that it shifts out as the speed increases. So at higher temperatures, we have access to higher speeds for our molecules. And since this is the same sample of gas under both curves, notice as it shifts out, it has to squish down in order for the area under the curve to represent the same number of particles as we have at 80 Kelvin. So just an FYI, you will be expected to know how to draw or interpret this kind of graph. Alrighty, so now that those are the 5 assumptions, let's go ahead and talk about the gas properties and relate it back to KMT. And you're going to start to notice some patterns. So one thing we know gases do is that they expand to fill their container. And if you look at this picture over here, imagine this. This is a container. This part right here is a movable piston. If we move the piston back, do you expect the gas particles to stay in that fixed square shape? No, that's illogical. So we know that they will expand to fill the container. But you know my favorite question, why? Why does it do that? Well, we have our 5 assumptions to choose from, and you'll notice there's going to be a pattern. Constant random motion, CRM. If they're always moving, they are going to have access to this space over here. There's no reason why they're just going to move here. They will move over here until they fill the container. And they also have no IMFs, no attractive forces, to hold them within this position. Unlike a liquid, which does have some IMFs holding the molecules in place. And this is just another picture of that constant random motion, CRM. Fluidity. Basically, that's the ability of molecules to flow, to move within the bulk properties. Why? Guess what? No attractive forces. And constant random motion. They are always moving, and so the attractive forces aren't strong enough to hold them in a fixed position like a solid, like you saw in the animation the other day. Low density. Why? Guess what? Gases have constant random motion and no IMFs. Are you detecting a pattern yet? Compressibility. That means that we can take a gas sample and squish it together pretty easily. And why? Can anyone guess? Molecules are far apart because of, you got it, constant random motion. They're constantly moving and no attractive forces, no IMFs. Don't know why that's covered, but on my other one it works just fine. But anyway, gases also effuse and diffuse. Basically, it's just 2 different definitions on how gases spread out to fill a container. And it's one's through a pinhole, one's just spreading out. So why do they do that? Can you guess? 3 letters, CRM, constant random motion, and no IMFs, no attractive forces. If I were to ask you this on Monday, I hope you would catch the pattern now. No, they've got CRM and no IMF. Alrighty, so those are some properties. Now let's talk about an ideal gas. An ideal gas is something that will follow those 5 assumptions of kinetic molecular theory 100% of the time. There are no deviations, there's no IMFs, constant random motion, they don't occupy volume, etc., etc. However, we know that gases do have volume, just really small, and they do have IMFs, just that they're moving so fast. So we do have a term called a real gas that deviates from kinetic molecular theory. Why? Like we just said, they do have IMFs, and they do have volume. Normally, we don't have to worry about this because they are moving so fast, but if we pressurize a gas and we push those molecules together, and if we cool it down so that they're not moving as fast, when they do come into contact with one another, they're moving slow enough that the IMFs do start to interact with the molecules. So we see real behavior at low temperatures and high pressure. Now, if you want to learn more about this, then that's where you will join AP Chem next year. All right. So a little section quiz before we move on to the next thing with properties of liquids and solids with KMT. According to KMT, the particles in a gas A attracted to each other are in constant random motion, have the same kinetic energy, have significant volume. So think for a sec, and the answer is constant random motion. I hope you got that. That would seem to be a pattern. All right, next question. What allows expansion of a gas? Low density, collisions between gas particles and an object, constant random motion, or attraction between gas particles? Think about it, and I hope you got it. Constant random motion. That's right, ladies and gentlemen. I think you're detecting the pattern. Alrighty, third question. Elastic collisions results in constant random motion, conservation of kinetic energy, molar mass of the substance, or loss of speed. Think about it, and not trying to trick you, but if you're paying attention, it's actually the conservation of kinetic energy. All right, moving right along. This would have been a warm-up in class. So looking at this, what we're doing is we're comparing two different gases. Hydrogen gas, it's just little 2.02 grams per mole, and krypton, which is one of our bigger noble gases. So what we're going to do, notice it does say these two gases are at room temperature. So the temperature of the two has got to be the same. They're both at the same temperature. Their molar masses, obviously hydrogen's really small, krypton's higher. Now, if they're at the same temperature, one has a smaller molar mass and one has a higher molar mass. Let's think about that 1/2 mass times velocity squared. They both have to be the same KE because they're same temperature. So the smaller gas, the lighter gas, will be moving a lot faster than the heavier gas, which is lower. And then for kinetic energy, kinetic energy is just a measure, or temperature is a measure of kinetic energy. So since their temperatures are the same, kinetic energy has to be the same. 10. Alrighty, moving along again, let's talk about liquids and solids. So gases we just talked about, and we're going to go into a lot of detail in those in just like next week and the week after. But let's do a little bit on liquids and solids, which we will revisit in the following unit. So what we're going to do here is, at this point, if you want to sketch this table and then do it yourself, pause the video right now and do that. The purpose of this is to review, can you identify the IMFs in these different compounds? So assuming you've paused and you're ready, if you didn't pause, that's fine. Let's just go through this together. We're going to start with our oxygen molecule right here. Now, since it's both oxygens, they both have really high electronegativities, but they're both the same, 3.5 and 3.5. So do they have polar or nonpolar bonds? And the answer is nonpolar, because they're both strong, but they're pulling equally, so they cancel. If it's a nonpolar bond, we should have a nonpolar molecule. If you remember from class, if it's a nonpolar molecule, there's only one thing it can have as far as IMFs are concerned, and that is your LDS, London dispersion force. Dipole-dipole is for those permanent dipoles, and H bond is when you have hydrogen bonded to phone. Alrighty, I exposed it already, H2S. If you look at the electronegativity values, it's actually all the bonds are nonpolar. So even though it's a bent molecule, there's nothing to pull. So if it's a nonpolar bond, nonpolar molecule, LDF. Easy peasy. Now let's get into carbon dioxide. We've seen that a couple times this year, actually many times. And when we draw that carbon double bonded to two oxygens on either side, the carbon's double bonded to an oxygen here, carbon's double bonded to an oxygen here, we know the carbon-oxygen bond is polar. Carbon's 2.5, oxygen's 3.5, so that's a 1.0 difference in electronegativity, so definitely polar, pulling towards the oxygens in opposite directions. So they have polar bonds, but if it cancels out because they're pulling in opposite directions, that will be our nonpolar molecule. If it's nonpolar, now it doesn't matter that we have polar bonds. What we're looking at here is the nonpolar molecule. What's the IMF or IMFs? You have one choice. Anytime it's nonpolar molecule, all we have is LDF. All right, let's go ahead and look at water, which is very similar to H2S. Up here, we're just doing oxygen instead of sulfur. And in this case, oxygen does have higher electronegativity, 3.5 versus hydrogen's 2.1. So that's a 1.4 difference. Definitely, H2S was bent, but the bonds were nonpolar. H2O is bent, but the bonds are polar. So it's a polar molecule. Now, what kind of IMFs does it have? Well, every molecule has LDF. And then we have dipole-dipole for sure because it's a polar molecule. And then the last thing you ask yourself is, does it have hydrogen bonded to fluorine, oxygen, or nitrogen? In this case, it definitely does. So we have hydrogen bonding. Alrighty, our last molecule. Now, if you were to draw this one, you would have the carbon in the middle. You would have a hydrogen, 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 and a chlorine coming off on the other side. It would be a tetrahedron. So there are nonpolar bonds for sure, but we're asking, are there polar bonds present? And the answer is yes. Chlorine is, I believe, 3.0. Carbon is 2.5. So that's a 0.5 difference. Just barely polar, but it is polar. So and there's only one chlorine, so there's nothing to cancel it out. So we do have a polar molecule. Now, what do we have as far as IMFs are concerned? LDF for sure. Polar molecule, so dipole, dipole. And then, do we have hydrogen bonded to fluorine, oxygen, or nitrogen? And the answer is no, so there's no H bonding. So that's the kind of process you're going to have to be able to go through in order to be successful identifying IMFs. Alrighty, let's talk about properties of liquids, and then we'll move to solids, and then we'll be done. So, liquid properties, NKMT. How do we explain the properties of liquids using kinetic molecular theory? High density. Well, remember, gases had low density because constant random motion and no IMFs. What do liquids have? Well, they're closer. So why are they closer? Because their IMFs are stronger than the kinetic energy factor. But they're at a lower temperature. Now, if we were to heat them up, that sign would switch and the IMFs would not be strong enough. But when it's a liquid, the IMFs are stronger than the temperature / kinetic energy factor. The fact that they flow, just like with gases, the IMFs are not strong enough to hold them into a fixed position like in a solid, because they're at a temperature where the kinetic energy is enough that some of the IMFs are breaking and some are still there to hold it in the liquid form. Then we move into incompressibility. So gases we could compress. Liquids are already dense enough that they, for the most part, we cannot squish them together anymore because they're close together, because they have IMFs. Next we have, and this looks kind of like our Skittles experiment, diffusion. Now gases will mix in a container. Liquids, if you combine them, will mix. Why? Why will they spontaneously mix? Why did the Skittle colors move? Why did they flow? Guess what? Yep, you guessed it, CRM. Because the molecules are always moving, they are destined to spread out as much as possible. But it's going to be slower than a gas because the molecules are denser, so they're colliding a lot. They don't have as much space to go straight and then collide. So they're working their way through that jumble of molecules. Surface tension. So surface tension is essentially coming about at the surface you have stronger IMFs that are holding the liquid in place. Like water has hydrogen bonding. That's what allows us to have the water bugs walk on water, etc. So, and the stronger the IMF, the higher the surface tension. That's what makes water so special. Alrighty, so this is just a picture. So if you have high surface tension, that means those molecules want to really be with one another. They're not attracted to a surface. Medium surface tension is in the middle, low surface tension. So like when you're Scotch guarding something because you're making it waterproof, all you're doing is spraying the surface of your substance with something that the water is not attracted to. It'd rather be within itself. And you that's why it bubbles up. Alrighty. Let's go ahead and talk about vaporization. So vaporization is an umbrella term. Kind of like polygon could mean a square, a rectangle, a hexagon, a triangle. Vaporization just means taking a liquid to a gas. That's it. Now there's two more specific terms that we do have to make sure you understand the difference between. There's evaporation, which is the surface particles of your non-boiling liquid going into a gas form. So think about if you had a cup of water on your nightstand for a month. You go back to that cup after a month and you haven't touched it, most likely the water will be gone. Why? Well, the idea is that even though the bulk water is just sitting there, those surface molecules, statistically, you're going to have some of them that are vibrating enough that they will break all those IMFs holding them in the liquid form and they will vaporize. But the bulk liquid doesn't do anything, just the surface. Boiling, however, you have added enough heat to the whole bulk sample that every single one of those molecules potentially has enough kinetic energy to spontaneously form a gas. That's why you have bubbles in the middle. If you ever watch a boiling pot of water, the bubbles form at the bottom or within the bulk properties of the liquid. So that's boiling. All of them, the surface and the body molecules, have enough kinetic energy to escape the IMFs. Alrighty, that's all of liquids. Now let's move to solids and we will be finished. So solids, again, we can explain it all with KMT. Definite shape and volume. Why? Strong IMFs. So the IMFs now, as a solid, they're now cool enough that that kinetic energy factor is really weak compared to the strength of the IMFs. 2, definite boiling point. That's because when you're heating up, that's the point where the kinetic energy and the temperature is strong enough to break those IMFs, and now they kind of start to flow. Some of the IMFs are breaking, some are still intact, but there is a definite point where that kinetic energy is an inflection point where it's strong enough to start breaking IMFs. High density, well, that's because they're packed close together, because the IMFs, they're strong enough to hold them in that fixed position. They still have some kinetic energy because they're vibrating in place, but it's not strong enough to break the IMFs. Number 4 is incompressibility. Very similar to our liquids, they are close together because they have strong IMFs compared to the kinetic energy factor. And then number 5, low rate of diffusion. That means it's not going to spread out. I hope you know that that is because they have strong IMFs. If their IMFs are strong, they're not going to be able to break apart, like even on a liquid on the surface. Many solids do not do that. Alrighty, that's it. We are done. Thank you for listening, and I hope you watch this video so we can get started on Monday with some fun stuff.